Now, I ended our last video a little bit too quickly on chapter 3.1, but this page is just all about finding domain of functions. So it actually is nice to have it a standalone video because we'll just talk all about these different variations of your domains and your restrictions. So we know that the domain of a function is the set of all input values for the function. The domain can be stated explicitly. So sometimes you might be given a function that is telling you that it only wants your x values between certain values. So between 0 and 5 equivalent. So from our graph, so we may or may not know how to graph this one, which if you don't, you can just pick a series of points starting at 0 and going all the way to 5. Now, if you already know what this visual looks like, you might be just tempted to say, okay, this is really a parabola. Without any restrictions on its domain, it should look like this. However, if we now restrict it to be when x is between 0 and 5, 0 to 5, it is cutting your graph in half and restricting it to certain values. So it's going to take a portion of it. So really your new graph, if you were to plot it, should look something like this. And we can go ahead and put that on your graph as well. I might not plot all of them. We have 0, we have 1, we have 2 and 4, 3 and 9, so somewhere up here. So it kind of looks something like this, but it's going to end by your 5. And let's just say, even better, we'll just do this. 1, 2, 3, 4, 5, all the way up to 25. So your graph is going to cut off. There we go. So there's no arrows to suggest that it goes off your page. It really just stops after the 5. So we're going from 0 to 5. Now, other times we might not explicitly tell us what these restricted values are. In which case we have a few different variations. And this comes all from your algebraic expression. So again, it just says if the function is given by an algebraic expression and the domain is not stated explicitly, then by convention, the domain of the function is the domain of the algebraic expression. That is the set of all real numbers for which the expression is defined as a real number. So what it's trying to say there is we don't want any undefined or non-real numbers stated in the domain. So let's consider the following. The one below it, it says f of x is equal to 1 over x minus 4. So we're trying to look for, okay, the values that will cause an undefined or an unreal response. Now, when you have a domain, or sorry, a denominator, so any sort of rational function with a denominator underneath, you're going to have values that are not going to work. Now, what number is never allowed underneath the domain or underneath the denominator? Denominators, we do not want to see have a 0 in that response. So if we take a look here, right, at x minus 4, what number will cause a 0 under here? So if x is equal to 4, that means if we did 1 over 4 minus 4, which equals to 0, we have 1 over 0. Is that allowed? No. So the only number that we have to restrict is going to be when x is equal to 4. Now, what is that going to look like? Well, on your number line, we're going to suggest, okay, 4 is this value. And if we don't want to be at this value, we're going to jump over 4 to skip over 4. So in a visual sense, what would be your domain? We're going from negative infinity. We're going to travel all the way to 4. We're then going to jump over 4. So union, and again, jumping over 4 to then infinity. Now, the more complex your response is, so if you have a bigger polynomial, you might have to factor. If things cancel and simplify, as we saw in chapter 1.8 and 1.4, if you cancel, you're going to end up with a whole. Wholes matter. So any sort of denominator, we want to find what is going to cause a 0 and exclude it. So let's try that again with A. Well, with A, let's take a look at simplifying, factoring. You have an x minus 3, which doesn't factor. Well, let's take a look at below. We have x minus 1 and an x plus 1. That was from the difference of squares. So if nothing cancels, we can go ahead and ignore the numerator if nothing cancels, because the numerator will provide us with your x-intercepts, but it's the denominator that's going to cause an issue. We want to know what values will be set, will be a 0. So if we have x minus 1 and x plus 1 is set equal to 0, because that's going to cause an issue, then x minus 1 and x plus 1, what will cause a 0? Well, if x is equal to 1 and if x is equal to negative 1, both values will result in a 0. So that means you would have a 0 in the denominator. So these are the two values that you have to skip over. So you have negative 1 and 1. You're jumping over these values. So what does your domain look like? Negative infinity to negative 1, union. Between these two, union, and then 1 to infinity. The more jumps you have, the more little pockets you're going to get. Now, what these are, which we're going to be learning how to graph these rational expressions, what you've just found, these are your vertical asymptotes. All right, let's try it with a different variation. So now we have g of x is equal to the square root of x. So with the square root, that comes with some hiccups with your x values. Now, what is not allowed underneath the square root? Well, negatives aren't going to be allowed underneath the square root. So no negatives numbers under the square root, which means if we were to write that in a mathematical sentence, right, no negatives. So does that mean 0 is okay? Yeah, no negatives just means you cannot have anything on the left-hand side of your x value. So that just means everything from 0 on is okay. So x is greater than or equal to 0 is how you say no negatives. 0 to infinity. And now this is only one variation, just like this one was one variation. You can have all sorts. So let's try that again under B. Now B looks like it has a little bit more to it because you have 5x. Now let's say the rest of this wasn't there and I said, can you graph 5x? Well, 5x, here you could say plus 0. You're starting at the origin and you go up 5 and over 1, up 5 over 1. So you have a line here. So this x has no restriction, no issues. However, the second piece of this, we have a square root sign, which is going to cause an issue. We said square root signs, no negative numbers underneath 3 minus x, right? No negatives, we said. That is when x is greater than or equal to 0. So we get to set everything underneath the square root sign greater than or equal to 0. So let's go ahead and solve that one. So you could subtract 3 to the other side. Negative x is greater than or equal to negative 3. Now, perhaps it's been a little while since you've done an inequality, but if you multiply or divide by a negative, and that is attached to your variables, so if multiply or divide by a negative, we flip the inequality. So to get rid of this negative 1, right, if it's starting out as greater than or equal to, we then switch it to less than or equal to 3. So that just means 3, if we put in a 3, right, are we allowed to be 3? Well, it's less than or equal to, so we get a closed dot on this 3. Because keep in mind, square root of 0 is okay. So if we have 3 minus 3 underneath the square root, it's the square root of 0, so that's okay. If we go over here and we say, okay, 3 minus, and over here, let's say is 4, we get the square root of negative 1. Is that okay? Not okay. So over here is not okay. Over here is okay. Square root of 3 minus 2, because 2 is over here. So the square root of 1, which is 1. So that part's okay. So we're going to be shading over to this side. So your domain goes from negative infinity to 3 inclusive. Now let's combine these two ideas together. So in part C, we have h of t. And notice that in your numerator, do we have anything to worry about in your numerator? No, it's just t. There's no square root. There's no funny business going on. So we can go ahead and ignore this. However, there's two actions going on. We have your denominator, which what values aren't allowed in the denominator? So whatever the number is down below, we don't want it to be equal to 0. So no zeros below. Okay. But you also have the square root sign. So the square root, if we have whatever is underneath, we said, well, what isn't allowed underneath the square root? No negatives, greater than or equal to 0. No negatives, greater than or equal to 0. So if we were to bridge these two gaps together, if we combine them, combining these ideas, well, one says no zeros. Still a little too big. One says no zeros, and the other says, well, it's greater than or equal to 0, right? The greater than is okay, but that one says equal to 0. So now, if you have 1 over the square root underneath the denominator, we're just going to say, okay, this is really greater than 0. It's a threshold number. You cannot be equal to 0 anymore. So if we have t plus 1, instead of saying, okay, greater than or equal to 0 as we did in the past, we said denominator can't have equal to 0, so we're just going to take away that equals to sign. So we have t is greater than -1. And if you're confused at all, you can always plug in your response and see if the values around it are going to be correct or not. So for example, let's try it when t was -1. So if you have 1 over the square root of negative, what was it? -1 plus 1, you have 1 over the square root of 0. So 1 over 0. Is that allowed? No. So -1 is not going to work. You can also try it on either side. You could do -2. You could also do 0 over here. 1 over the square root of 0 plus 1. 1 over the square root of 1. 1 over 1. And that's a number, right? That's a real number. Try it again. 1 over square root of -2 plus 1 is 1 over square root of -1. You now have a negative underneath the square root. Again, not okay. So this side does not work. So figure out what your threshold value is, and you can always test values that are around it.